So, show of hands. Who here has a deployment system? Who here likes their deployment system? Out of the people that have their hands raised, did you write that deployment system? Yeah. How do your developers feel about it? So, part of this problem is that, in general, deployment is a generally ignored problem. It's one of the first things you build at an organization. And it's usually one of the things that you build when you're going to scale. Like you have an application that's running on a single server, or maybe a few servers. You can go into the systems, you can deploy those. But at a certain point in time, you hit a point where like, now it's time to scale. I have to run this on like 10, 15, 20, 100 servers. And at that point in time, your code has to run everywhere. So what ends up happening is you do your initial deployment system. It's not very good. You go back to working on your application. Your deployment system is at a point where it's working. You don't really need to make much changes. And then you start scaling your people. And now you have like 20 people doing deployments hopefully. And when it gets to this point, then you have to change your system again. And an iterative process occurs. And eventually you get to a system that's kind of okay. It's not great. It just happens to be one of those things that no one wants to touch. You usually have one person that writes it. And so let's use Wikimedia as an example of this. Wikimedia Foundation is about 10 years old now. Well, Wikimedia is 10, 12 years. And so when it started, it was completely volunteer-based. All of the roots were volunteer, all the developers were volunteer, all the editors are still volunteers. And a couple of the people that started all of this, of course, wrote a deployment system early on. And that deployment system is called SCAP. Sync Common All PHP. This system is an rsync and parallel SSH system. There is a single deployment server, and on this deployment server runs an rsync daemon. Under the rsync daemon are a set of repositories, and inside of these repositories you can run deployment commands. The most prominent of which is called SCAP. When SCAP runs, it tells a tier of rsync servers that are in every single rack that are on a single application server to pull the changes from the deployment server. And then after it does that, it tells all of the hosts to then pull from the tiered rsync servers. This system works. It's not great. There's a number of downsides. One is that it has poor immediate consistency. And so this means that although it's running parallel SSH, it's running rsync to get everything into a consistent state. Rsync and parallel SSH do not really work very well. An entire SCAP deployment based on our current system can take up to 30 minutes across all of our systems. And during this, it can't do a full fan out of parallel SSH because it'll overwhelm the rsync servers. Also, there's issues with running very large numbers of SSH commands through a single SSH agent. So the length of time that this takes is bad because you have some sets of systems that are in one state and other sets of systems that are in other states. So you have to make sure your application is very fault tolerant for very lengthy deployments, which means it needs to be very forward and backwards compatible. And this includes things like schema changes and such, which can be very problematic. Also, it has very poor reporting during deployment. It's basically a wall of text. It shows you all of your errors and all of the successes. And since it's using SSH, there's also the ability that some of the SSHs are occurring, and they're just sitting there. They're not actually doing anything. The system's overloaded. And so during this, you're not actually getting any real information about what's failing. Additionally, there's no reporting after deployment. So once you do a deployment, you have no idea of the state of your systems. Hopefully they're all in a good state. We've actually had a number of outages due to this. It sucks. I think a lot of deployment systems end up having this problem. But it's definitely something that is nice to not have. It's also relatively difficult to modify and maintain. It's a bunch of bash scripts. It just runs SSH commands. The bash scripts have to exist on both the deployment server and all the hosts. And we maintain these via Puppet. We're not using Salt exclusively. We're using a mixture of Salt and Puppet currently. A full Puppet run across our entire infrastructure takes quite a long time because our Puppet servers get overloaded and can't run it all at the same time. Also, we tend to do eventual consistency with Puppet. So in this situation, it can take up to 2 hours to change deployment system if you need to for some reason. It's also not very extensible. So although it's a bunch of bash scripts that you can just go and modify, this only actually currently works for MediaWiki, which is our core application. We can't deploy any other applications with it. So it's extensible in one way, but realistically, it would have to have a full rewrite to work with any other applications. Also, there is no service orchestration. So in the situation where hosts have failed for some reason, if a host has failed, it takes a root level action to depool these hosts because we use a separate service to actually do depooling of hosts and monitoring health checks and such. And developers don't have root level access, so they can't make those changes. Additionally, it's relatively difficult to use. In the 4 years that I worked at Wikimedia Foundation, I've never actually learned how to use the full system. This is why. This is just a small set of the scripts that are used inside of the deployment system. And this is because iteratively, new scripts have been added to do individual things. Since the system is rsync based, you don't have to do a full rsync of the data. You can do individual directories or files, which is why you have things like sync common file and sync common all. You have sync file, you have wiki reviews, etc. There's so many things in this. But this also lends itself to some really horrible problems. Since you're only doing like very small portions of the deployment, there's a possibility that one engineer is making a change, and we use a Git workflow. So someone pushes in a change, they pull it to the deployment server, and then they only push out part of their change, not knowing that they have left out a part because they haven't done a full copy of the code. So when this occurs, you have another person that comes behind them and does a deployment, and then their deployment blows up. And we've had outages where one person does a deployment, and then like 4 hours later, someone does a deployment, and it all comes burning down, and you have to page ops because they have no idea why it failed, and you have to debug it. It's terrible. There are a couple positives about this system. It does have eventual consistency. We do eventual consistency through both Puppet, and we also do eventual consistency by ensuring that the service, Apache, is not running unless a deployment has actually occurred and it's running the current version of the code. So even if a deployment fails at some point in time, it will eventually go back into a proper state. Additionally, it has a very fast transmission mechanism via tiered rsync. This is very good for very large binary files. So given the positives and negatives of this system, I decided to write a new deployment system that uses Salt instead of SSH, and that uses Git instead of using rsync. So this is a general overview of the system. It's written into 3 parts. There is a Git front end, which is just an extension to Git that uses Python called Trebuchet Trainer. That interacts with the backend system called Trebuchet. It is a SaltStack based system. It's a 2-phase deployment system that uses both fetch and checkout, which then synchronizes the code to all the hosts. And it writes this information back into a database for all of its deployment information, and there's a web interface that you can use to see the current state of all of your hosts in the deployment, the current tag that's running, etc. So a more in-depth overview of this is that similar to our whole infrastructure, we have a deployment server. This is a Wikimedia-specific thing. All of our repositories are open to the world. We let anyone modify our software and infrastructure. So we can't deploy directly from our code review system or our Git server. So we have a place where we pull all of the code before it gets deployed, and we deploy from there. In other uses of this software, the deployment system isn't actually necessary, but it is in this. So we have a deployment server. It runs Apache. We have a set of Git repositories underneath that. Inside of the repositories, you can run Trebuchet Trigger commands via Git deploy. And when you do a deployment, it talks to a salt master. It talks specifically to a runner, which figures out, based on this repository, find the set of minions that are targeted for this. And then it will run custom modules on the minions, a deployment module. When that runs, it either does a fetch or checkout stage. When that stage finishes, it returns its information using a returner to Redis that lives in the deployment server. At that point in time, the person using the deployment system can see the information about what has occurred. So during the fetch stage, you can see like, all right, this is the number of systems that are still left waiting for this fetch to finish. When it finishes, they move to the checkout stage, they get information that says, now everything's done checking out, you can go on, it finishes, and your deployment is done. All of that information is also accessible via the Ricochet web interface by reading from Redis. So there's a number of really great pluses that are positives that you get from using Salt for this. And one is that the immediate consistency is actually very good. By breaking the deployment into 2 stages, fetch and checkout, you can do a fetch across all of your systems, which pulls all of the objects and makes sure that everything is available on the system first. And then when you go to the checkout stage, it's a single call across all the minions that immediately does a git checkout from one state to another state, making the relative atomicity of the deployment within seconds across all of your systems. It also has eventual consistency using states. At Wikimedia, we're actually using Puppet for this too. But the system is designed to use states by default. It also, of course, has reporting via returners, which means that even though I'm using Redis for this, there's the ability to use other things. You can use MySQL, you can use Mongo, you can use whatever you feel like using for your returner for the system. Additionally, the modification of the system is actually very easy. Since it's just a set of modules, returners, and runners, etc., you have the ability to very quickly change your code and deploy to all of your systems, since Salt has a mechanism for distributing its modules and such. Additionally, all of the service orchestration that you get from Salt, you also have available through your deployment system. You can do reactors. So for instance, if hosts fail a deployment, you can send an event that automatically deploys it to another service. You have runners that can do things where it does the deployment. During the deployment stages, you can say, well, I'm going to deploy this, and then this cache needs to be flushed because of that, and et cetera, et cetera. And then in the modules, you also have the ability to call other modules and do other things inside of that. Additionally, you can target it a number of different ways. You can use grains, you can use pillars. And also the configuration is also very nice because you can just do it through pillars as well. So here's an example of a pillar configuration for deployment. There's a global configuration portion that is the deployment configuration. It just does things like it tells it which database to use, basically. In this case, Redis is the return that's being used, so it configures Redis. In this case, it also says all deployments are going to occur under a specific parent directory, so that you always know where the code's going to be running from on the system. And then you have repo-specific configuration. In this situation, we have a test repo. It's being targeted via grain, which is test repo. It also says what its upstream is. So in this case, it's pulling straight from our Garrett server. This is not actually how we run in production. This is just an example. And so that's where its code is actually coming from. And then there's also some hook points in the system itself during the fetch and checkout stages. In this example, at the end of the fetch stage, it's going to refresh its pillars using SaltUtil, so that in the checkout stage, we can use those pillars for some other reason. There's anything you can do here. You can pass in your own custom modules, you can pass in arguments to the modules and everything. Similarly with the checkout stage, the code gets checked out, and then on the servers it regenerates in CSS using like Compass or whatever thing is you're using to actually do generation of things. You can do template generation, etc. You can run maintenance scripts when it checks out. And then lastly, there's the ability to define a service name that is associated with this. So for instance, if you're running an application that spawns a daemon, you can have, like this one is a daemon that runs test service. You can use Trebuchet Trigger or other actions to do things like service restarts, reloads, etc. There's, of course, a couple negatives with the system as well. Git's really slow for large binaries. Also, just putting binaries in Git is a terrible, terrible idea. So deploying binaries via Git is not a good idea. The good thing is the system is written in such a way we don't actually have to use Git. The only real requirement is that you have a two-page deployment, which is fetch and checkout. And since it's using Salt, it's pretty easy to replace the portions of the system that are using Git with another module that implements the same interface. And also, nicely for this, I have a colleague that yesterday, before I finished writing these slides, started fixing this problem by using Git annex. So it's still possible to use Git to do the deployment, but your actual binaries can come from a number of sources in the backend. Additionally with this, there's currently no canary support available. This is just something that I haven't added to the system yet, but all of the points that have to occur completely, or you have to break them up into places via targeting. But this is easy enough to add. You just add another grain or build it to a system that says this is a canary that would do that. So for the interface for this system is Trebuchet Trainer. And it's just an extension to Git. It has a series of commands that you can run. Start or starts a deployment. Sync causes the deployment to actually synchronize the code across the systems. Abort stops a deployment if you decide that you don't actually want to do a deployment. Or revert will go back to a previous state. The way this works is it actually does tags for all of the deployments. So if you want to revert, you go back to another tag. Since the tag already exists on all of the systems, the revert is just the checkout stage and it takes seconds. Then there's also a set of service actions, restart, reload, stop, start, etc. Similarly, there's also a reporting mechanism so that you can see the current state of either the current deployment or a deployment that has already occurred. And the system itself is extensible, so you can write your own modules or extensions to this, or any action that you want. For instance, at Wikimedia, we have something that we called scat traps before. And our whole deployment system is basically like, this thing is going to kill you if you actually deploy it. And that's usually something to do with schema changes. So at Wikimedia, we have very large databases with lots and lots of rows and many tables. And some of the table updates, if you're going to actually update the schema, can take weeks. So we generally do rolling schema updates across all of the databases, from the slaves to the masters. And during that period of time, we might have some code that's actually required to be, that requires that schema update to actually run. So in that situation, we have something called scat traps, which tell people this is going to break your deployment. And in this situation, one of the extensions that we're considering is adding like a scat traps action to this, which will look at Git notes inside the repository to say like, this is flagged as something that will break your deployment. You have to manually say, yes, I already took care of this. But that's just one example of an extension that you can do for this. All of the default actions are also completely extensible or changeable. It uses a driver-based system for all of that part. So here's an example of a deployment. It's relatively simple. You start your deployment. At that point in time, it takes a lock. Only one person is allowed to do a deployment at a time. After that, the user does whatever they're going to do, Git pulls or whatever they're going to do to bring it in a specific state that they want to deploy. Then they do a sync, which brings it to the fetch stage. At this point in time, the fetch is finished. There's 0 minions pinning. So the user continues. It goes to the checkout stage. Similarly, the checkout finishes, no minions pending. It finishes, releases the lock. So another way of looking at the same information is to use the web interface. The web interface, this is written in Flask with Angular and Bootstrap. It has the ability for you to watch multiple repositories. It's pretty often where there's 2 code deployments that need to occur at the same time because they have dependencies on each other. So in this system, you can take a lock in both repositories, or wait for a lock to become available, since in this case, the bottom one has a deployment already started. And then at that point in time, other people can see that you have locks on your repositories and such. And as the deployment occurs, this web interface immediately refreshes as the stages occur. So all of the stuff that I've described so far really kind of assumes that the system is already in some kind of build state and that you're doing a deployment to things that have already been configuration managed and built by ops. At Wikimedia, all of our deployments to production are hardware. We don't use virtualization, we're not using containers. So in this situation, the system has been built around this. But we also have a virtualized environment that is being used for test and development and semi-production uses. So the basic mission of Wikimedia Labs is kind of a weird one. And it's that we want to enable the world to treat Wikimedia's infrastructure like any of its projects and that anyone can edit. So you go to Wikipedia, you hit edit, you enter some text, you hit save, it's immediately available to everyone else. And by making it so easy to actually change Wikipedia, it makes it so that everyone can actually be editors and write an encyclopedia. And so we feel that our software and our infrastructure should be the same way. So we've built an infrastructure for Wikimedia that is virtualized using OpenStack. We have the OpenStack infrastructure itself, which is labs, it's production maintained. And then inside of that, we create projects for users. And these are based on real-world projects, where the projects are specifically OpenStack projects, which in the AWS world would be like accounts. So inside of these projects, users can create their own instances. They can manage DNS, they can manage IP addresses, etc. But they also have access to the Puppet infrastructure. They can take the Puppet code, it's open source. They can modify it, they can run it against their infrastructure, they can build new infrastructure, and then they can take those and they can push it into code review. We review their code, and then we push it out to production. This gives us the ability to let random people on the internet make root-level changes in our infrastructure. Since the inception of labs, we have accepted, we have contributions from probably a few hundred developers, many of which are not staff. They're just trusted volunteers. So inside of this environment, deployment becomes more of a problem. And realistically, the majority of these people that are doing work inside of labs aren't even doing infrastructure changes. They're really wanting to do media development. And so in this, they don't want to do infrastructure. They don't really even want to manage like MediaWiki itself. They want to write their code. They want to push it out. That's it. So our concept that we've been looking at is extending the deployment system to be more of a Heroku model of deployment, to where you have your infrastructure declared inside of your repository itself. So in this situation, Salt makes this relatively easy to go about. There's Salt Cloud, which you can define a set of infrastructure with. So in this situation, you would define the infrastructure inside of your repository using Salt Cloud mappings or just a YAML or something along those lines. When your master would have a checkout of all of the different repositories, it would read, it would watch the files to see if they have any changes to Salt Cloud. If it did, it would regenerate the infrastructure as defined in the cloud infrastructure. And additionally, since it's just, since it's all connected in with your configuration management and such, you also have the ability to say, well, this infrastructure is going to be running these states. So you can have a set of states, and you can also then have like custom states, custom modules, custom returners, etc., that all go through the Salt-based systems inside of your repository. And then you can have your Salt master say, well, I'm going to extend my modules directory to also be in all of these repositories as well, same with the pillars, states, etc. And that way, if something doesn't exist in the global portion of the system for a developer already, developers can define their own infrastructure first, and then have those things slowly moved into the global system for use for everyone else. So I have recently moved from Wikimedia Foundation to Lyft. I've upstreamed all of the changes for Trebuchet Deploy. It's in GitHub. It's Apache licensed. I definitely invite everyone to come help with the system. Also, Lyft and Wikimedia are hired in case anyone is looking. I'm available on IRC, on Trebuchet Deploy channel, and my contact information is up there. Also, as I've mentioned, Wikimedia is using both Puppet and Salt, but Lyft as well. So when we're using it this way, we're using Puppet for configuration management, because we have tens of thousands of lines of code in Puppet. It's very difficult to move all of that immediately over to Salt. But we are using Salt for remote execution. We're using it for orchestration and things like that. So there's quite a bit of work that needs to occur for those systems to actually work and talk together. So I have a talk later today, which I hope to be a discussion where hopefully I can get people involved with getting some of the work done for integration between Puppet and Salt. I think it would be a very good way to move people from one system to another. So please come join me in that. That's, I think, at 10:45 in Amethyst. Anyway, thank you.